Today, we are joined by a company called ActLight. Now, they have something called, and I have to read it because otherwise I'll forget it, dynamic photodetector. So we're in the world today of these things, wearables. Look at that little light shining out, going up against something, sending its data back and being detected and understanding what's going on. And ActLight have got a very disruptive technology, and they're going to tell us all about it today. So welcome to Roberto, welcome to Sergei. Tell us today, if ActLight didn't exist and I was dealing with one of these and I was trying to understand how the data goes from out and then back in, how would I be solving that today if you didn't exist?
Without ActLight existing,
Yes.
Guy, the issue is that that the market player knows very well. It's impossible to go into other wearable like this one, an earbud, or like this one, like a smart ring, with ultra low power consumption that at the end of the day is what is needed for these battery operated devices. So the industry got stuck to move from that kind of wearable, like this one, the one that you show of wrist wearables, got stuck when want to move vital signs monitoring into hearable devices and smart rings.
So we're all in. We're vital state monitoring, but we're all about understanding that we have to be low power because we live in an absolute low power. But that issue has been being dealt with as the power's got lower and lower and lower. Today, they are solving that problem, but obviously you are disruptive, and our platform is all about disruption. It's saying we can do this better. So could you just go into some granular detail about today? If you are solving that problem today, what would be the infrastructure to get that low power that you could do? And the reason why I asked that question is so that the community can absolutely understand and recognize, is this me or isn't me? I know it's obvious that it's wearables, and I know it's obvious that it's light. I know that. But just go into the granular detail that explains what goes on there so that we can see very clearly when you talk about what you do, because it's a very differentiator. It is a disruptor. Explain what they would be seeing today and what they believe to be the norm, and then we'll move on to how you do it.
When you want to monitor heart rate and then derive through algorithms other vital signs, you need to have photodiode, at least one, maybe more. Then as a separate block, you have another chip, which is an analog front end, which include also other blocks to drive the LEDs and so on. And then you have one LED at least or more. So that's the state of the art. With our technology, we simplify the system because our dynamic photodetector is manufactured with standard CMOS technology. And for this reason, it can be integrated into a single chip, into an ASIC, where the front end and all the other necessary block are included. So one single chip to have all the necessary blocks except the LED. Then with that, maybe Sergey can add on more details.
You're describing where you'd have maybe three or four parts of the component in a discrete system. So that's the legacy design that everybody would understand. And then moving on to what you do is you've created where we're using your CMOS technology and your design, where you bring that into one single. Would I describe it as a module? Is that a way that you would describe it? A one single module that does all three of those things together, but just with one chip.
It's two things together. The third is LEDs that cannot be integrated into a CMOS chip.
Okay, so Sergey, should we talk a little bit more about how you then actually do that, so we can then understand the difference between those individual discrete solution and then talk about how you do it with your individual module?
No, first, in additional to what Roberta explained, with our dynamic photodetector, we can reduce also photodetector size, and also it means we can reduce total size. We can do this. It's because of this idea, dynamic photo detector. General problem with existing photo detector, it's output signal. Output signal is a photocurrent, and this current is weak. There are some ways to improve this signal. For example, using avalanche photo detectors. In this case, you can have high output signal, but drawback is very high voltage needed to have avalanche detectors, like can be 50 volt or 100 volt. And idea behind of dynamic photo detector was have detector having very high output signal, but still operated at low voltages. Normal voltages you are using in semiconductors, like 1 volt or 3.3 volt. So this was idea, and we end up with this device called dynamic photo detector. And due to this feature, you don't really need complex circuits. You don't need amplifier, for example, because output signal is already very high. This greatly simplify circuits, simplify chip design, and in additional, this will increase performance. More precisely, signal to noise ratio is better in our case because you don't have noise introduced by amplifier. Basically.
Right. Okay. So now you use the word dynamic. Which part of that? Because that's a very strong word to use, dynamic.
Yes.
And you've done that on purpose. So when you use the word dynamic, what do you mean when you use that word dynamic?
Yeah. Normal photodiode, which was invented long time ago, it works at a fixed voltage. You apply reverse-based voltage to photodiode, and what you measure is photocurrent, and you keep this voltage constant. This is why we call it static. But this, like everybody is using this without using this word static, but we are called it static. Why we are different? We are not keeping voltage constant. We are switching polarity on diode from reverse to forward. And diode, it's a device which has low reverse current and very high forward current. And we are measuring when forward-based voltage is applied to this detector. This is why output signal, it's a forward current, and it can be milliamps if needed. It can be very strong. So this is why you don't need amplifier. It's already digital.
Yeah.
And this is why we call it dynamic. We are to do measurements. We are switching polarity from reverse to forward.
Yeah.
We are not keeping voltage constant. We are switching. And what we are measuring, we are measuring time when forward current starts. And this time is light dependent. By measuring this time, we can extract light intensity. So it's totally different approach.
Absolutely. Okay. All right. So today I understand what Roberto described, and I described, and I think the watchers will understand your different approach. But when you're talking about low power, the way that you're able to do that is because you haven't got that constant voltage going on. You're using your word dynamic. You're only sensing it at the point that you need to sense it. So it's almost like an on and an off. So you're only using power at the point that you need to, rather than constantly.
Yeah, it's one point, but the second point, output signal is very, very strong, and this is why you don't have noise introduced by circuits, by sensing circuits, because our output signal is already very high. You are not limited by this kind. You can do what you want. It's very easy to sense.
Okay.
Circuits become very simple. you don't need any amplifier, and you are not creating additional noise.
Okay, so we understand that part. Can you now just describe? So you've described how you achieve that low power. There must be benefits though in the way that you then get the message coming back and the signal that you get back. So how does your way of doing it benefit on the actual data that it gets back from the light that it receives? What are the benefits of doing it that way, other than the power benefits?
Okay. This really we need to consider by application. For example, in a heart rate measurements, basically, when you show smartwatches, this is a heart rate monitor. Device works like this. You are sending light by using LED, and you need photodetector to detect reflecting light. And power consumption is coming from LED. This is the main source of power, light source. And when you're reducing light power, your limit is noise. When you are measuring heart rate signal reflecting light, you are limited by noise. And by reducing this noise, which you can do by using our photodetector, you also can reduce input light power. So, and what does it mean? It means you can reduce total power consumption.
If the way that you do it, you're sending less light and still getting the same signal back, you're still getting the same data and the same nuance that you need from the data that's coming back. You basically describe two ways that you save power using your solution. First one, if I'm to understand it correctly, is the fact that you're not living in this constant state. You're living in a state where you're only sending when you need to, which is the dynamic part. And then the second bit is, because you're doing that, you're sending less light, but which is going to use less power, because that's the main way that you burn power in these systems. But because you can send less light, don't think that doesn't affect the amount of data and the importance of the data that's coming back. You get the same outcome. Essentially, is that, in summary, what you are doing and how you are doing it?
In general, I think you're right. Still, important part is why we can do this, because our output signal is very, very high. It's digital already.
Yeah,
this is an important part.
Yeah, I don't think I hope I didn't give the impression that I thought you were compromising that part. I didn't think you were compromising the output of the light. I think that was clear. I think you made it clear that you weren't compromising the output of the light, and that the clarity of what comes back, or the integrity of what comes back, is exactly the same way, because you do it in you described it, because you do it in a digital way.
Yeah.
So, okay, good.
Maybe easy explanation. It's basically you have light source and you have photodetector. By improving performance of photodetector, you can reduce light needed to still have a good signal.
Let's be honest. What you're doing is, we have this T-shirt. Which I haven't got on today, but we describe sometimes, when we come across things that are really, really complicated, that they're alien technology. That's how we kick off with, that can't be of this earth. And when you're doing stuff like you're doing, which is complicated CMOS technology, using light, using different ways of doing things, you really are breaking the barrier of how legacy and how people do it today. You've almost completely reinvented how you do it.
Yeah,
I think it is a completely different approach. So what we want to do then is encourage the community to say, wow, that's interesting. So the last question is, I'm in the wearable market, I'm in the medical market, I'm trying to understand how I can apply this technology. When you're doing something brand new like this, the most important thing is that they need to be able to evaluate it. So how does somebody come to you and understand how they can look at how your system would work with their current legacy?
Very good question, Gay. So there are two things that we do every day to follow up with incoming leads and customer inquiries. One, the first thing we do usually is we set up a meeting, either in person if possible or through internet meetings. And during that meeting, we do explanation like we try to do here, but more important, we fire up our demonstrators. Demonstrators are object like this one, which is a rudimental wrist wearable with our detector on the flip side, or hearable the earbuds like this one. This is a earbud demonstrator with our detector in it, or same thing. Sorry. Okay, we also have this one way. Sorry for that. Same demonstrator as a real perfect. Here we go. I promised I show it. That's
fine. No. Yep, there you go.
Okay. So that's what we do. Usually, the follow-up of that kind of meeting is that the prospect client ask to have one or more of these demonstrator in their lab for their own testing, and we do sell our demonstrator to them. Usually, it's a customized one because let's say the appetite of the clients out there is always different one to each other, and we are able to basically customize the demonstrator to allow the clients to see what they want to see, basically, or to match with their labs equipments that are already there. So demonstrators are available. We sell them to interested clients. It's usually a stepping stone to licensing our IP to them.
Yeah. So let's just ask one last question, because I think that's an important point that you make there. They're licensing the technology. They're going to have a sensor partner that they probably work with today.
Yes.
So how does, obviously, when you send out your platform for them to look at how that will work, how easy is it to integrate with what they currently have, with their current infrastructure in their system? Because obviously you have a partner that you send out your IP embedded in. Yes. How difficult is it to integrate from one thing to the other?
Not at all.
Not at all. Okay.
Not at all. I'm talking about experience. If we talk about the wearable device and the vital signs monitoring as an application, one of our licensees is very advanced in that process. They do have a product that will be shortly commercialized, made it commercially available. And for them, it was not difficult at all to integrate our DPD into the ASIC that perform vital signs monitoring. The reason is that they are already into that market. And basically, with our technology, we provide incremental design, meaning detector integrated into the front end or into the ASIC, VSM ASIC, and they already own all the other blocks, and they own or they can do CMOS technology, and so for that reason, is not difficult at all. One thing that maybe we didn't emphasize is that our dynamic photodetector is produced with plain vanilla or standard CMOS technology. So that's make things very easy. Far we produce it with 6 different wafer foundries. Some of them are customer owned wafer foundry. Some other are the well-known located in Taiwan. And so also this is important to say, the IP is manufacturable through standard CMOS available to anyone.
Yeah. I think just in that simple statement of that paragraph you just said, if you're covering off our friends in Taiwan and you're covering off 5 other foundries, I think we can safely say that your CMOS IP is manufacturable. Yes. So one last question. This has been very much about changing the way that people do it currently, and you've very much focused on the using less power. That's very much the thing that you focused on in this discussion, because we're obviously talking very much about power. Are you able to say generally, and if you or how do you describe it when you go to meet a wearable manufacturer or somebody working in the medical world? Are you able to talk in terms of overall power usage? Are you able to talk about overall power battery saving? Are you able to talk about percentages? How do you succinctly say, if you go over to our process, we will save you X?
Cool. So we have a very precise answer to that question. It 10 times less power consumed by the vital signs monitoring sensor. And it comes from what Sergey mentioned and what you very well, Guy, what you have summarized, which is you need much less light to have the same quality of signal.
Took me a while to get my head around it, but once I understood, yes, I was able to.
This was perfect. The way you described, we can use it as a marketing claim. Anyway, so to your question, 10 times less.
10 times. That's massive. That's huge. That isn't just I've changed the world physically how you're gonna do it. So I'm saving you space, I'm saving you power, I'm saving you. I heard a new phrase yesterday, which I'm going to use because it makes me sound intelligent. Changes system topology if you start taking off components and doing it one simple way. Obviously, that self-describes itself. But if you're able to actually, I mean, this won't be a claim. This will be true because you will have all the data to back it up. 10 times is just mind-blowing.
It is, and it is what is needed to go into this kind of wearables, because if it is more, the power consumption increase the temperature that you feel when you wear, and basically burn the battery energy to the point that need to be charged 3 times per day, which any user, including us, don't want to do.
No.
10 times, and this can be demonstrated when we fire up this kind of device in front of a customer. They can see the LED power, basically.
Right. Very
and
good.
They can see the quality of the output signal at the same time.
Okay, very good. Well, Roberto, Sergey, this has been amazing because, as I said at the start of this discussion, the whole point of our platform is all about disruptive technology. Now, disruptive technology can be, just a bit better, just a little improvement, something that we didn't necessarily have today, but we can have tomorrow. Sometimes it's a big leap. Sometimes it's a big leap. Sometimes it's something that you go, wow, we absolutely have to look at that. And then sometimes you get the real word disruptive come along, where somebody says, I can improve something by 10 times. That doesn't happen very often. So I think that by definition of our platform, and by definition of our community, you've been absolutely fantastic guests with introducing your ActLight company, your technology, and we look forward to seeing how you move forward and you change the world of these and how they communicate with the world and how you save power. So thank you very much.
Thank you very much, Guy. Thanks for the opportunity.